To begin this section, we probably should take a look at partial derivatives. Now, I know we're not going to do any partial differential equations, but the idea of partial derivatives comes a little bit handy here. And also, by the way, sometimes you might see your differential equations look like this. Well, they kind of look like this. So this is called a differential form. If you remember back in Calc 1, there's this idea of a differential. Or when you do a u substitution, when you say u is equal to something and then you take the derivative of both sides, you technically come up with differentials. And those differentials are really just the derivatives with the d, whatever it is you're dealing with. So the dx and dy here are part of the differentials, and when you put them as a fraction, as a ratio of over each other, then you get your dy dx, or dx dy, depending on whatever thing you're dealing with is asking for. So anyways, back in Calculus 2, I don't know if that's back in Calculus 2 or if you haven't taken it yet, looking forward to Calculus or Calculus 3. Back to Calculus 3 or looking forward to Calculus 3, there's this idea of partial derivative. And if you have a function of two variables, you could take the derivative of that function with respect to x or with respect to y. And the formal definition of a differential is that you would take the derivative with respect to x and then multiply that times dx, and then take the derivative with respect to y, multiply it by dy, and then add them both together. So this is the formal definition of a differential, which again is just some theoretical background that you don't really need to know for what we're about to do. But if you have taken Calc 3, you should try to remember when that happened. If you haven't taken Calc 3, then this is a definition that you'll run into. So what they're saying here is that there's a case where if the function was equal to a constant, then the differential can be given by taking the differential of the left-hand side, which will give you the left-hand side, the differential, and the derivative of a constant c is 0. So what we have here essentially is a differential equation. So that differential equation, what we want to do is we want to backtrack to try to obtain the original function where we have x's and y's, and then if we're so lucky, we might even be able to solve for y, in which case we would have an explicit solution. Now, if we're not, or if we don't care to solve for y by itself, we would have the left-hand side of this having x's and y's combined. So if we leave it like that, then it would be what we would call an implicit solution. And we did talk a little bit about that. Okay? So that's the Calc 3 background. Now back to our class. When we're dealing with a differential equation, we can, if somehow we can write, or is given to us, the differential equation, actually this should say is equal to 0, is an exact differential equation if it corresponds to some function f of x, y. I'm sorry, I don't think there's a 0 there. So what we need to do is we need to basically use some Calc 3 techniques to try to obtain the original function f. Now, this is the formal definition of an exact differential equation, and that's another way to categorize a differential equation. But according to this definition, we would have to solve for it first to be able to figure out if it's exact or not. Or we need to know f of x first. But really, that's where we're going to. So we need another criteria to try to figure out if a differential equation is exact. And so that criteria is given in a theorem. And the theorem says that in your differential, if we can find a relationship between m and n, these two functions, then, and if the relationship happens to satisfy this equation where the partial of m with respect to y is equal to partial of n with respect to x. If that's true, then we can say that we have an exact differential equation. Okay? So this is it. And then what we're going to do is we're going to use some Calc 3 techniques to solve for f, to find our original function f given this differential. So I guess first we need to figure out if, or how to check if a differential equation is exact. So let's take a look at some problems. I think let's take a look at the book. And let me just copy a whole bunch of these, and then we can decide which ones to do. Let's do well, it's always nice to do number one, right? Let's do number one and see if it's exact. So this will give us some practice on taking derivatives, taking partial derivatives. So we have to assume that the m is the one next to the x, and we want to take the derivative of that with respect to the other variable, y. So that's the key. So m, the first function, take the derivative with respect to y. So the derivative of m with respect to y, and when we take the derivative with respect to one variable, we treat the other variable as if it was constant. So x is constant with respect to y, and the derivative of a constant is what? So this is 0. And then the next thing we want to do is we want to take a look at the second function, n. That's the function next to the dy. And we want to take the derivative of that with respect to x. So again, we take a look at this function, take the derivative with respect to x. Y is constant, so this whole thing is constant, and the derivative is constant of a constant is 0. So they're equal. So we can say this is exact. I don't think so. I think it's okay if they're equal to 0. I hope so. All right, let's try another one. And take the derivative with respect to x and with respect to y incorrectly, then it would be wrong. Yeah, so if you take the derivative with respect to x, this is 2, this is 3, and they're not equal, that doesn't mean anything in terms of both differential equation or Calc 3.
For the one that has a dx in front of it, that's the partial with respect to x, and you take the partial to that with respect to y. And on the other one, you take the partial
If you switch to dx dy, then you just have to remember that your m function is the one next to the dx. And then your n function is the one next to the dy. So what Evan said was from Calculus 3, and he paid attention in class. And the idea there is that if you have a function of x and y, which is what we're pretending that we're dealing with, f of x, y, the second order mixed partials are the same. So derivative of f with respect to x and then with respect to y should equal to the derivative of f with respect to y and then with respect to x. So that's why this would be exact. But like I said, that's the Calc 3 version of it, and that's something that you can take a look at in Calc 3. But I didn't want to spend too much time on it. So, Alan, I think the question was switching the dx and the dy.
I'm trying to break it is what I'm trying to do.
Oh.
Let's see why it works.
Oh.
So I'm trying to
Well, why it really works is kind of Evan's explanation. And we can, okay, let's do some Calc 3. So this is the idea, is that this is your m and this is your n, right? And the theory in Calc 3 is that if you have a function f of x, y, then the partial of f with respect to x first and then with respect to y, so this is essentially the second derivative, but we call it the second order mixed partial because you're mixing the x and the y. And then if you take the derivative of f with respect to y first and then with respect to x, that those two functions should be equal to each other.
Since our m and n are already first partial derivatives.
Yeah, so m and n are already the first order partial derivatives. And in fact, this fx over here is your m, and this fy over here is your n. Then these two should be equal to each other. So there's also other mixed partials, fxxx and fyy, but those don't play into this. And like I said, if you've taken Calc 3, you're familiar with this, with the second derivative test, where you have to take the second derivatives of things. But, you know, like I said, for this class, we won't worry about that. Okay. So back to this idea of m and n and my and nx. Let's do this one. Take the derivative of this with respect, this is your m. Take the derivative of this with respect to y, and the 2x is gone, and then the derivative of y is just 1. Now you take your n and take the derivative of this with respect to x. And so this is a 1, but there's a negative sign in front, so that's a negative 1. So those two are not equal to each other. So this is not exact. Okay? I took the derivative of this function with respect to y. And 2x is a constant, so that's gone. The derivative of y with respect to y is 1. So my is equal to 1. And then now I take the derivative of this with respect to x. So I treat y as if it was a constant, and all I have is x here, which is 1. But there's a negative sign in front of that, so that's a negative 1. So I have nx is equal to negative 1. Now, unfortunately, 1 does not equal to negative 1, so our conclusion here is that this differential equation is not exact. Okay? All right. We do one more, and then we'll pick one, so let's do two more. The derivative of the first one over here with respect to y is what? 4. The derivative of the next function with respect to x is what? 4. So this is exact. All right, pick one. 4, 5, 6, or 7. 6 has a missing parentheses or something. Maybe it goes over here. Anyways, pick one. 4, 5, 6, or 7. 7. The derivative of the first function here with respect to y is what? So it's negative, right? 2y. And the derivative of the second with respect to x is what? 2x. There's more, because this is, y is a constant, remember? Minus 2. Y is a constant, so we need to attach that also. So if it was better to look at 2y times x, and then take the derivative of that with respect to x, where y is constant, then it's just going to be whatever that constant is. So here we have not exact again. Okay, get the hang of this? All right, let's do 6. What? Last one. Oh, I didn't get that. A soup Nazi? What?
I'm sorry, it was a bad reference. I immediately regret it, but I was just thinking that of him asking for one more example and meaning like, no.
A soup Nazi,
I was
okay.
like, no soup for you. But I didn't think the whole not calling you a soup Nazi.
It's okay. You can call me soup Nazi any day.
Trying not to be a hole any deeper.
All right, with respect to y, I see this, and then everything else is a constant except for, oh wait, I'm sorry, we need to do some arranging here. Because this isn't quite in the form that we need it to be. So what do, yeah, so there's a missing, anybody have the book? No? This is a PDF of the book, so when it PDF'd, it might have lost the parentheses, and I don't know exactly where the parentheses should be. What page is it?
2.4.
69. I mean, suppose I could pull it out of the WebAssign. So it goes over here. So dy dx is multiplied by this whole thing. All right. Okay, so it looks like I need to rewrite this so that it looks like that differential in differential form. So I think the key here is to multiply everything by dx. Yeah? So if I multiply everything by dx, I'm going to have a 2y minus 1 over x plus cosine 3x. And this is going to be the dy. So now my dy looks like it's going to come up first. So I need to be aware of that when I assign my m and my n. I have a y over x squared minus 4x cubed plus 3y sine x, 3x dx equal to 0. Should I rewrite it so that dx is first? Okay, so if we don't rewrite it as dx is first, just remember that this is your m, the one next to the x, and this is your n, the one next to the y. So what is it again? My. I need to take the derivative of this thing with respect to y. So y is a constant, 1 over x is, with respect to y is the variable, 1 over x is a constant, 1 over x squared is a constant. So the derivative of that is just a constant times y, or derivative of constant times y is just a constant. The derivative of the second term will disappear because there is no y's in it. A derivative of 3y is 3. Oh, no, this is 3y times this. 3 sine 3x. Does that look right? That's the derivative of m. All right, let's go to n with respect to x. Derivative with respect to x, the 2y is gone. I have a negative here. Derivative 1 over x. Negative. No, that's an integral. Derivative. This is x to the negative first power, right? 1 over x squared. And then there's a negative in front of it, so can we just write this? Positive 1 over x squared. And then the derivative of cosine is? Negative sine. Oh, it was so close. But it's not exact. Because one has a plus, one has a minus. Unless we did something wrong. No, I don't think so. Yeah. Exact means that the derivative of the first term with respect to y is equal to the derivative of the second term with respect to x.
It means we can integrate this, we can integrate both of these directly, and they should both give us the result.
Yeah, so
were they the same function at one point?
Yeah, so that's what it is. So they were the same function at one point. We took the derivative with respect to one variable, and we took the derivative with respect to the other variable, and that's how they came up with this. Now, we want to check if they did in fact come from the same function of x and y, but instead of integrating right away, we can do a criterion check to see.
If it comes out as exact, that means you can
That means
one function that'll beat
yes,
this criteria.
yes. All right. When we integrate C, yeah, it should be the family. Yeah, it'll be the same one. Okay? So not exact. Sorry. So this is just to check whether something's exact or not. We haven't done the differential equations part yet. So we're going to do the differential equations now, where we try to obtain the original function. And again, back to Calc 3, if we know that the first function, m, was a derivative of an original function with respect to y, maybe we can take the antiderivative with respect to y and get the original function back, right? So that's what we're going to do. And let's use one of these for an example. Let's take a function or a differential equation that we saw was exact. So let's take number 1 and use that. As our first problem. So we already know that this is exact. Now, this is m, which theoretically we're thinking of as the derivative of some original function with respect to x. And our task is to try to obtain the original function. So what we could do is we can take this m function and then take the antiderivative of this with respect to x to try to obtain the original function. And so if we integrate this with respect to x, we're going to get, is this x squared minus x? Right? Now, let's be careful with the c business. And the c is a constant, but this is constant with respect to x, which means the other variable, y, is a constant with respect to x. So it's possible that we have a function of y involved here. So let's place, instead of a constant c, let's place c parentheses y to say that there's a possibility that there's a y in here that would have disappeared after we took the derivative with respect to x. Okay, this is your potential function. And in Calc 3, it's literally called your potential function. So now, how I normally do it, how I like to do it, is I take my n function and then I take the derivative or the antiderivative of that with respect to y. But they do it a little bit differently. They do it in Calc 3 differently too. So I'm going to see if I could do it their way. So what they do is that this is your potential f of x function. Now, according to them, your n is equal to f sub y, right? According to the theory of this. Your second function was the original function whose derivative is taken with respect to y, and that's what gets placed here. And so that's what we're assuming. So what we want to do is we want to take your f function, which is potentially this, and take the derivative of this with respect to y. So with partial derivatives, they use this funny looking d, the curvy d, to say that I want to take the derivative of my f function with respect to y. So what is that? Well, the x's are constant with respect to y, and then all I have here is cy. Oops, not equal, but plus. Let's make this the derivative. And that's what n is equal to. So n is equal to c prime of y. Wait, what's n equal to? In our problem, n is equal to 3y plus 7. Right? So then this will give me a chance to get cy if I just integrate with respect to y. So this will be, what is it, 3 halves y squared plus 7y. Now I can put a c, which is a true constant. What do we have? we have our f of x is equal to x squared plus or minus x plus cy, but cy we found to be 2 or 3/2 y squared plus 7 plus a constant. Okay? Is this your answer? Yeah. Oh, yeah. Thank you. There was a y there. It was just really small. I couldn't see it. Is this your answer? No. Not quite. Remember, your answer has to be in the form of f of x is equal to c. So actually, this c over here can be brought over to the other side. So let's remember that your answer is of the form f of xy equals c. And so if we write down our answer here, your answer should just be f of xy, which is x squared minus x plus 3/2 y squared plus 7y equals the constant. Now that's your answer, and that's your family of curves that would satisfy this differential equation. Okay? Now, if you could solve for y by itself, you can try to do that, but then we will lose a few things. You can see that this is probably some sort of a circle type equation. So you'll do a plus and minus something. You'll have to complete the square, do a plus and minus something, and then you have to restrict your domain so that your domain only includes what's defined in the circle. But at least we were able to find a solution. And then if you have an initial condition, then you can pinpoint where your function should be. All right? Does that make sense? Okay, good. And do another one? Let's put a box around here, just so I'm clear. All right, let's take another one that was exact. Number 3 was exact. Oh, too bad 6 wasn't exact. That would have been fun.
All of this is still part of example 2.4.
Yeah, 2.4. Number 3 looks like it'll turn out to be the same thing. Let me look at the book and see if I can find other ones. Let's try number 22. It has an initial value, so that will give us some idea of solving for C. So we're going to assume that this is exact. I mean, we should check. Let's check. This is number 22 from the textbook. Did it in your head already? It's e to the x, or no, it's 1 and then 1. Yeah, it's exact. Let's just double check. Oh, let's just write it out. So m with respect to y is equal to 1, right? Because x is constant. And then n with respect to x, there's a 2 gone. There's y e to the y, which is gone. So this is just going to be 1 again. So this is exact. That's good. That means we can continue on and solve for this. All right, so what was the process? We assumed that this comes from an original function of two variables, x and y, and that the first function, the one with a dx, was obtained by taking the derivative of this with respect to x. So we're going to undo that derivative with respect to x, undo the derivative of this thing, which is e to the x plus y, and then take the antiderivative of that with respect to x. Now, antiderivative e to the x is x. The antiderivative of a constant, what's the antiderivative of 2? 2x, right? So antiderivative of a constant is going to be the constant times x. So this is your antiderivative. But we also have to account for the possibility that we have some other function of y that disappeared because we took the derivative with respect to x. Okay? So now we're going to say that this is your potential function. You're going to take the derivative of that with respect to y. And we should get the n function. So the derivative of this thing with respect to y, the derivative of e to the x with respect to y is what? So I'm going to explicitly put a 0 there, right? Because I'm looking at this derivative here, 0. The derivative of y times x with respect to y. So x is a constant, y is a variable. This is like saying 2x, the derivative, or 2y. So the derivative is just going to be x. And then now we have another possible set of all kinds of y functions here. Take the derivative of that with respect to y and just call it c prime of y. So this is a derivative of your function, potential function with respect to y. And now let's just rewrite what n is equal to. So now I have this equation. And I want to solve for c of y. So it looks like the x's can cancel. So I have c prime of y is equal to 2 plus y e to the y. Now we have to take the antiderivative of that. I know the antiderivative of the first one. Now we need the antiderivative of the second one. How do we get the antiderivative of that? Integration by parts. So do that in your head. U equals y, dv equals e to the y, du is going to be equal to 1, v is going to equal e to the y, and so uv minus the integral of v du, but the integral of e to the y is e to the y. Done. See? You guys are integration by parts experts now. Or do it on the side of your notes and make sure that that's correct. Plus c. Actually, we could just put the plus c at the end because we'll toss that c over to the other side anyways. Yeah, it's kind of important that you know how to integrate in our class. And like I said, simple U substitution, integration by parts, and later on partial fractions are the most important parts. Did anybody check if this is correct? You guys just gonna believe me? Okay.
I mean, you answered one, so.
Oh, I was expecting somebody to write it down. Thanks, Susanna. All right, we have our cy function that can go in this place where our potential function was sitting. So our function now, our solution, f of xy. Actually, let me write this down because this is the form. And so when you actually write your function, let's just write down the whole thing, set it equal to c. So this is e to the x plus yx plus cy, which is 2y plus y minus, or times e to the y minus e to the y. And the plus c over there says that we got a family of functions. We have an initial condition, so we can use this initial condition to identify our one particular solution. Again, solving for y is not the ideal thing to do here, so we're going to want to just keep it as an implicit solution. All right, now that we have our initial condition, let's go back to solving for our unknown c, the arbitrary constant. And we can read this, right? This is our x value is 0 and our y value is 1 from our initial condition. So if we go ahead and put 0 in for x and 1 in for y, we should be able to solve for c. What do we got? We got a 1, e to the 0 is 1, plus 2, plus e to the 1 minus, or e to the 1 is e, minus e equals c. So c equals 2, 3? I got 3, right? E minus e is 0. 1 plus 2 is 3. I got 1 from e to the x, and I got 2 times 1 from there. And the 1, yeah, e to the 1, e to the 1. Okay, so we got c is equal to 3, and so finally your real solution, your particular solution, your particular unique solution is going to be given by this implicit function, e to the x plus, I'm going to change the xy to yx, or yx into an xy, plus 2y plus y. Wait. 2y plus y e to the y minus e to the y equals 3. Okay? Wow. That was a lot. So, we have a solution, a particular solution. You want to see the graph of this?
Yeah.
So I don't know if I remember how to do the differential slope fields here. Well, let's see. What if I just type the solution and see what happens? E to the x plus x times y plus 2y plus y times e to the y minus e to the y equals 3. So you can see that this is not a function. Doesn't pass a vertical line test. So our point, what was our point again? 0, 1. So I think with this point, you can have this to be defined. I don't know if this would be defined for all real numbers, because this function starts to overlap each other at -3. No, negative. Oops. So I think your function might be restricted from -2 until, I think it goes on forever on the positive side. So, because there's this weird asymptote here, I think your function has to only go from -2 to maybe infinity. Yeah, so that other piece that looks like it might make it not a function breaks off at -2. Uh-oh, something's happening. I'm not doing anything. Stop. It's still going. It's zooming in. Can we stop? Abort. Abort. Close.
Well, then, if that first part has an asymptote, then the second part also.
It turned out that I don't think it does, because as I was zooming out, it looked like it kept on going. So I would probably, let me see if I can. Oh, whew, there it goes. This might be on a new page. So it looks like our solution to have this as a true function or solution would have to go from -2. To infinity. Okay, because on the left side of that, it becomes not a function. So that's something that's probably not easily seen just by looking at the function. You know, when you're looking at this function, you're not going to assume, oh, there might be an asymptote at -2, and it's not a function on the left side of -2. But that's something that you can explore with some sort of graphing program to see. They don't ask for that in the homework or in any of the stuff that you do, but when you're playing around with this on your own in your free time, then you might want to consider looking at the graph so that your functions exist at that particular interval. Okay? All right. So I think maybe that's good. If your differential equation is not exact, there might be a possible way to make it exact by multiplying your differential equation by some function that could possibly make it exact. Now, I don't know if you guys have any problems in your homework with this information, but this is not something that I probably, it wouldn't be something that I would test you on. But I think since we did talk about integrating factors in the previous section, it's worthwhile taking a look at an integrating factor to make something exact. So this integrating factor is a new function that would make your differential equation exact if it wasn't already. So let's take a look at an example. Let's see how easy this is going to be. Let's take a look at an example where we have a problem that wasn't an exact differential equation, and let's find an integrating factor for that. Now, I don't want to go over the reasons how they got the integrating factor, but these are two possibilities of finding the integrating factor. So if you take the combination of my minus nx divided by n, and you see that that will end up being a function of x by itself, then you can define your integrating factor by this expression. And then there's the other possibility. All right, so for this, I'm not going to attempt to make up my problem. I'm going to see if the book has any problems where you need an integrating factor. Okay, number 37 is an example. So let's first verify that this, in fact, is not an exact differential equation, which it shouldn't be because they're giving it to us as a problem that's not exact. So our m and our n functions should not work when we find the derivative of m with respect to y and the derivative of n with respect to x. And these are the derivatives that I got. The first one is going to be 0 because there's no y's in it. The second one is going to be 2x times y, and then the 4y is gone. So clearly this is not exact, right? So now what we want to do is we want to find the ratio of this thing to see if any of them would turn out to be a function of just one variable by itself. So let's try my minus nx divided by n. So my is 0 and nx is 2xy, and you divide by n. Oh, that doesn't look nice. So is that a function of x alone? I don't think I can simplify to make it into a function of x. So I'll try the other one. So the other one is nx minus my. So nx minus my over m, and that is going to be 2xy minus 0 divided by m. M is equal to x. And this is equal to 2y. So yes. Yeah.
Just take the y's and factor them out of the top one and make that x.
Oh, will it work?
I mean, you take the y out of the bottom plane and you cancel out the
Oh, that would have worked, huh?
I thought so.
I didn't even bother. I went to the second one because it looks like it would be easier. And if you were to do that, you would get minus 2x over x squared plus 4. So this could have worked, but I want to integrate that. And although this is...
It's worse, but it would be a function of
Yes,
x as well.
yes.
Okay.
So let's scratch that out and say, yeah, this would work. This works. Let me write it in a different color.
If you want to use it, another different question.
This works, but this is easier. Because 2y, I'd be happy to integrate that. I mean, you can integrate this one too, right? So u substitution is going to be an ln or something, but go for the easier one. Yes? Yeah, this is e to this thing, kind of like the integrating factor that we had. This exp means it's e to this power. Yeah. So then we're going to identify our integrating factor right here. So our mu, and let's take the second one. So it's going to be just a function of y. Mu of y is going to be equal to e to the integral of this easy function now that we just found, 2y, with respect to y. I think that's y squared, right? So that's your integrating factor. So somehow, if you multiply this differential equation by this, it'll magically be exact. I don't know if I believe that. Do you believe that?
Symbolically tell us what's going on there?
What we did was we found an integrating factor, and according to this setup, if we multiply this original differential equation by this integrating factor, then we would have an exact differential equation. I don't know how that's going to work. Does it look exact?
Try partial rule.
Yeah, well, let's try it and see. Check to see if exact. So this is your new n, now m. This is your new n. So let's take the derivative with respect to y, right? My equals, now x is a constant, e to the y squared times 2y, right? Now let's take a look at our n and take the derivative of that with respect to x. Well, e to the y is a constant. E to the y squared, sorry. And now take the derivative of this thing with respect to y. Or, sorry, with respect to x. This is going to be 2xy plus 0. Hey, it's exact. Right? These two are equal. My equals nx. So this is now exact. So now we could just solve for it like we did before. Are we good here? With respect to x. No, this now it's a piece of cake. What? Cake?
The original differential equation, if we move one of the variables to the other side, it becomes simple.
Yeah, I know. There probably would have been an easier way of doing it. It should. All right, let's do this. This is your M. And this is your N. Yeah?
I think actually for the N, if you pull out that Y,
Uh-huh.
it works with chain rule, right? E to the Y squared. So
Yeah,
it becomes
so-
e to the 2y, so it'd be 1/2 e to the Y squared.
Yeah, that'll be a simple U substitution
Yeah.
for us.
Yeah, I thought it was really, really hard.
Yeah, that's what I thought too. But
Yeah.
so what do? We find our potential function by taking the antiderivative of M with respect to x. And so e to the y squared is constant. I can just take that out, or I can just leave it there and say it's a constant. And the derivative of x is what? Or the antiderivative, the integral of x is what? 1/2 x squared e to the y squared is constant. And then that's it. Then I have a plus c, a potential function of y, right? Now let's take the derivative of that with respect to y. And this is going to be the 1/2 x squared is constant. The derivative of e to the y squared is e to the y squared times the derivative of y squared, which is 2y, plus c prime of y. Now this fy is supposed to be n, so we're going to set this equal to n. And for us to get this kind of prepared, let's distribute this out. So we have x squared y e to the y squared plus 4y e to the y squared. And this is your n. And we want to solve for c, so we gather the terms that look like they're the same. And then we say c prime of y equals 4y e to the y squared. And we want to find c.
It's just 2y e to the Y squared.
So if you do a u substitution, wait, what? 2 times e to the y squared, right? There's no y in there.
Oh, sorry. No, it's different.
I don't think so, because after you do u substitution, you get rid of that y, right?
You take the derivative of the top part of the Y
So
squared,
then
which
e
is
to
2y.
du.
Oh, yeah, sorry. No y.
So-
and
So this is your c, and this is your f function, so your final answer, or your f, is equal to, let me just write the answer, 1/2 x squared e to the y squared plus this extra y, function of y term, is equal to a constant. Yeah. And
just x squared e to the Y squared. If the 1/2 is multiplied by 2.
oh, I was looking at this.
Oh, okay.
All right. What was our initial condition? Y of 6?
No.
What was it again? Y of 4 equal to 0. So y is equal to 0, x is equal to 4. So let's solve for this. 1/2 4 squared e to the 0 plus 2 e to the 0 is equal to c. This is 16, 8, 10. C is equal to 10? Now we have our particular solution to our initial value problem. Okay? All right. So with the last 5 minutes of class, I want to invite you to go to the STEM Center. I know for people who have me for linear algebra, you guys already went. But if you go to the Learning Center and get a passport, how does a passport look like? Did you guys give it to me?
Oh, wait.
Yesterday. So, Jesse, hold it up again. This is a passport that you would get from the Learning Center. And what I want you to do is I want you to go, if you want, go to the Learning Center, get a passport, and have a few people sign it. Put your name on it and put Math 257, or what's this class? 270. 275. Thank you. And then give it to me at the Learning Center because I'm going to walk over there also. So if you give that to me with your name and have at least one signature on it, then I'll give you 2 extra points on the first exam.